All right, modeling with exponential and logarithmic equations. Now, in this lesson, I'm actually going to go into more detail than I would actually require in my class, and I'll point out the things that you won't see on your exam with me, or the things that wouldn't necessarily be required in my class, or how we'd be doing working with these as much this year. So that'll make more sense here in a minute, but I show everything because this is what the textbook shows, and some of the homework problems will reference a couple of these. So the first stuff, though, is information we should already have. I'm just going to make sure we've got it down. So a review of finite differences. Finite differences help us determine the type of polynomial function. If it's, for instance, if it's linear or if it's quadratic, okay? If the input increases at a constant rate, so in other words, as x goes up by a constant rate, in this case, this table goes up by 1. Could go up by 2s or 4s or 8s, whatever, 6, whatever. Okay, if the data is linear, if the first differences of the input are constant. So in other words, if I was adding the same amount every time, it's linear. If the second difference of the input, the second differences are constant, it's quadratic. And we'll see an example of that here in a minute. But we also know a data can be modeled by an exponential function if we have inputs that increase at a constant rate, and the outputs have a constant ratio. And when I say constant ratio, if you take the following, the second output, and divide it by the first output, so 1 divided by 1/2, that's 2. So really what's happening is you're multiplying by 2. And some of you may go, well, I don't even have to do that to figure out that I'm multiplying by 2. Well, this is a pretty easy pattern to see that you're multiplying by 2. Like if you're multiplying by 1.7, it's not as easy to see, and that's where you'd want to say, well, really the way I get that what we call a common ratio or a constant ratio is you take 32, okay, the second, so if you think it is like y sub 2, and divide it by 16, the previous, okay? All right, or technically, if you're thinking of a pattern, it'd be y sub n, and this would be y sub n minus 1. Now, that's getting really technical and stuff that you don't have to deal with, but you don't really have to know that notation. But you're taking this and dividing by this, taking this divided by that, that divided by that, that divided by, and so on. Okay, so this is an exponential right here. All right. So this next piece, let's go ahead and classify using that pattern there. So first thing I like to do, first I'm looking at the input. Input here is increasing by 1 every time. Okay, it's pretty easy to see. So the output, first thing I do is look for linear. Am I going up? Am I adding the same amount every time? So in this one, I'm actually decreasing by 5, and then I'm decreasing by 3, and then I'm decreasing by 1. So no, it's not linear. However, I don't see a huge change every time. So it could still be exponential. However, since I've already started looking here, I'm going to see if my second differences are the same. So there's the first difference. Second difference, yeah, -5 to -3 is 2. -3 to -1 is 2. Add 2. Add 2. Add 2. So the second difference is the same. So that's what I mean by second difference. Okay, we covered that earlier in the year. But second difference, that means it is quadratic. If the third difference was the same, it would be cubic, or third power. Okay? And so on there. So looking at this, notice from, by the way, here, we're adding 1 every time, again, so inputs are the same. But notice on my outputs on this one, I go from really big to quite a bit smaller, and then smaller, and then it starts decreasing at a smaller rate, or the numbers get closer together, if you think of it that way. When that happens, that's generally an idea that it's an exponential pattern. Okay, so I quite honestly don't know what 54 or 162 times what is 54. 54 divided by 162. I know I can't quite get that, but as I start looking down here, I start going, hold on, 2 divided by 6. Hey, this is 1/3. Okay, I'm dividing by 3, or I'm multiplying by 1/3 right there. So I can start asking, well, am I multiplying 18 by 1/3 or dividing 18 by 3 to get that? Yeah, I am. Now, we don't say divided by, we say multiplying by number in between 1 and 0. Okay. Well, notice 2 divided by 3, or 2 times 1/3, is also 2/3. So we start recognizing that, yeah, okay, that's 2/3, or multiplying by 1/3 every time. Okay. If you're not sure, you could do 54 divided by 162. And notice you're taking this and dividing it by this. You're taking that term and dividing it by the one previous. Okay, that's just the notation for that. Once again, you don't need to know that notation. You'll deal with it eventually in series and sequences. Not this year with me, but unless you get way ahead. Okay, but if I were to reduce that 54 and 162, what goes into both of those? Well, 9 does. Okay, and if you're like, I didn't even know 9 went into 162. Well, there's a way to tell that. 1 plus 6 plus 2 is 9, and 9 goes into 9. So, but if you didn't know that, you could divide by 2. They're both even, 27, and this becomes 81. In 27 and 81, I know that 9 goes into both of those. 9 goes into 27 3 times, and into 81 9 times. And 3 and 9, 3 goes into. 3 goes into 3 once, and 3 goes into 9 3 times. Now, someone may go, well, why don't I just use a calculator and divide 54 by 162? And I get 0.33333333. As long as you know that that's 1/3, I guess you could do that. Okay? So this is times 1/3. So all of that being said, this is exponential. All right, so we got quadratic, we got exponential. Now, anyone that knows anything about the way we teach this, a lot of times we're trying to show examples. Most likely this one's going to be linear. Okay, so I'm adding 2, I'm adding 2, I'm adding 2, I'm adding 2. This is linear. Okay, in fact, I already knew that since I wrote the problem. There we go, linear. All right. Okay, let's go ahead and look at some new stuff here. So we're going to write an exponential function using 2 points. So if you remember back to systems, this is kind of where you kind of hang your branch, writing systems of equations, and then also writing an equation in y equals mx plus b, knowing point and the slope. Okay, that's kind of what we're doing here. It's a similar process. So first thing I'm going to do is note that in order to write this equation, I need to know A and I need to know B. Those are the 2 things I need. Okay, I need A and I need B. What I'm given a value for x and a value for y. In fact, I'm given 2 values for x and 2 values for y. Okay, and so what I'm going to do is I'm going to write 2 different equations, because if I need to know 2 things and I can write 2 equations, then I can figure those out, as long as those are the 2 only variables in those equations. And given this, if I know x and y, I'm going to write one equation in the form of y equals abx. I'm going to say, okay, really that means if I use x and y here, that 8, that's y, is equal to AB to, well, 8 goes with 1 to the first power. Okay, so notice I've just substituted in 1 and 8 for x and y. And I'm going to write a second equation. The second equation is also going to be in the form of y equals abx. And actually, let me switch colors here, just try to keep it straight there. And that second equation is going to be using 3 and 72 for x and y. So 72 is equal to AB, and then x is 3. Okay? Well, I need to solve one of those equations for A. Okay, and I'm going to use the first one just because it kind of lends itself better as I'm working down the page. Okay, I'm going to go ahead and divide by b to the first. And by the way, b to the first is just b, right? I'm going to divide by b to the first, and remember, b to the first is just b, so I'm eventually just going to erase that first power. So a is equal to 8 over b. All right? And I know that these 2 points pass through, or this equation, or this line passes through these 2 points, so these 2 points are tied together. They're connected by a line or a curve. Okay, so that means if a equals this here, a is also going to equal that right there. So I can substitute that in. So really what I have now is I have 72 is equal to, and let's go ahead and stay with our color here, 8 over b, that's a now, times b to the third. Okay? And so from here, I'm going to start looking at this. I'm going to try to keep my color in play here, at least for just this one problem, 8 over b. And I'm going to write b cubed as a fraction. Now, b cubed as a fraction is just b cubed, or b to the third, over 1. Now, these are just two fractions that are being multiplied together. And remember, when you're dealing with fractions, you can cross-cancel. If this is b to the first here, and this is b to the third here, well, that means I can cancel out one of those b's. So what happens is this cancels, and this becomes a 2. Okay, if you're like, I don't get that, that means really you have 8 over b here, okay, and you're multiplying it by b to the third. Now, b to the third is b times b times b, right? And you just cancel a b. So you're left with b squared. That's what's happening right here. Okay, so really, I now have 72 equals 8b squared. Why is that important? Well, 72 equals 8b squared. Oops, I forgot my 8 there. That is actually really important. So let's not crowd the 8. No one wants to be crowded there. Okay. Then really, I can keep going with this problem. I divide both sides by 8. I get 9 equals b squared. And then I take the square root of 9 because I want to get rid of that. Now, usually it's a plus minus root 9 would equal b, which would mean b is equal to positive and negative 3. However, remember, when you're dealing with an exponential function, b has to be greater than 0. Okay, therefore the negative is extraneous. We ignore the negative and we just deal with the principal square root. So it's always going to be the positive value for b. So b is 3. Okay? I now know b is 3. I now need to figure out a. How can I figure out a? Well, you can take what you have for b, right, that 3, and you can go right back up here and put it in for b. Like this big vicious cycle, right? And so now I have 8 over 3 equals a. So a is 8/3. So my equation, y equals ab to the x, is y equals 8/3 times b, or times 3 to the power of x. Notice your equation can only have x and y in it, an independent and dependent variable. There we've got it. Okay? Now, I would encourage you to do this next one on your own before I try it, but I'm going to start it out here in a minute. So, let me see. So first I'm given x and y. You can always pause, by the way, and do that. And so if I'm writing this equation, I have 2. So y is equal to a times b to the x, or 4. So I use my first equation there. And then I'm going to write another equation. So I'm going to have 8. So 8 for y. So y is equal to ab to the x, and x is 7. I'm going to take one of those equations, and I'm going to solve for a. So I'm going to divide by b to the 4th. So 2 over b to the 4th is equal to a. I'm going to substitute that value in for a right here. So I get 8 is equal to 2 over b to the 4th times b to the 7th. And remember, this is like having a fraction. So those two things right there cancel, right? I have 3 or 4 of them here. I have 7 of them up here. That means I'm going to have 3 more left on top and none left on bottom. Those are going to cancel. It's going to become a 3. Okay, so I have 8 equals 2b to the 3rd. I'm going to divide by 2. So I get 4 is equal to b to the 3rd. Then I'm going to take the cubed root. Okay, so that means the cubed root of 4 is equal to b. Okay, and I'm going to round that off for the sake of this problem. We're going to call it, I'm going to go to 3 decimal places, so 1.5. No, let's go to 4. No, we'll go to 3. That's fine. 1.587. Okay. So that's our approximate value for B. So if we're, say we need A and we need B, we have B now. B is 1.587. Okay. All right. Now when I actually calculate A, I'm going to use my exact value. So that's the chunk that's going to, that's the chunk that's going to substitute in for that B right there. Okay, so A is equal to 2 over, okay, the cubed root of 4, all to the 4th power. Okay, now I kind of misled you in the way that I circled that. Really, this only goes in for the B. In fact, you know what? To maybe make that a little more clear, choose a different color here. So this is going to zip on in, going to go in right there, right? And so that was this chunk right here, the cubed root of 4. So the 4th power still remains there. Okay, and all that equals A. So that means A, if we actually do the math there, I'd just plug that into my calculator. However, you could do the math down here and kind of switch it around if you needed to. That is actually, remember, if you have a 4th power and you have a cubed root, the cubed root is your denominator, so you could write that as 2 over 4, the 4/3 power, if you wanted to. Okay, I don't know if that's necessary, but you do the math. A is approximately 0.315. Okay, so my equation, y is equal to 0.315 times 1.587 to the x. There, you've got it. Now that's an approximate value. If they actually want the exact values, if you're being asked to find the exact values, if that's the case, you're going to probably change this A to 2 times 4 to the negative 4/3 power. Right? That gets that fraction, that stuff out of the denominator. And that's your A term, and this is your B term. That would be an ugly answer. Okay, and probably not the best one to give, but I guess you'd have to round there. At least in my class you would. So there you got it. Okay, so hey, there's like there's 2 pieces left, and they're not that little, okay? One is to write an exponential model using a table. The other is to write a logarithmic model using a table. The logarithmic model is going to be pretty straightforward. We're going to use a graphing calculator. Exponential model, I would also use a graphing calculator, or I'd use the method I just showed you. However, the textbook goes into another method that makes finding the value of B more accurate. So I'm going to show that as well. All right, so first thing we need to recognize is there are times when you have a table and it's not exactly exponential. Like you start multiplying. For instance, on this table, if you were to multiply here, you would find that, okay, I'm multiplying by like 1.75 here. Okay, and here I'd be multiplying by like 1.71. Okay, I better maybe right at a slant. Okay, so 1.71 here. Okay, here I'd be multiplying by like 1.83. Here I'd be multiplying by 1.77. Here it's 1.77 as well. And here it's like 1.77 also. Okay, so it's pretty close to about 1.77 that you're multiplying by, right? So the reality is this is pretty close to exponential. It's not exactly exponential. All these are being multiplied by that. And remember, the way I find that is I divide the second one by the first one. Okay, and I find out that. Now, you may go, okay, well, it doesn't multiply by a constant, so we don't know B. Therefore, when we try to write y equals AB to the x, we can't find a constant ratio, so we can't find B. I graph it, and it looks like this, and notice it looks exponential, but it's a little off, and obviously we can see that here. So what we're going to do is we're going to find like an equation that best matches it, almost like a line of best fit when you're dealing with linear equations. Okay, so the first thing you need to do is find A and B. Well, we just did that, right? Or first thing, find A or B. But we just did that. Given 2 points, we were to find both A and B. Well, you're given 7 points. If you pick any 2 of them, and I'm just going to pick the 2 easiest ones, and say, okay, well, I know that the graph goes through 1, 4, and the graph goes through 2, 7. Okay, that will give me an approximate equation. So you just go through the same process we just went through, right? You try to find A, you try to find B, you use your equation, y equals ABX. You write 2 equations out, okay, so we have, I'm going to go through it fast because we've done it. So 4 is equal to AB to the first, okay, and another equation in terms of y equals ABX, we'd have 7 equals AB to the second. Okay, we solve one of them for A, so, or for A, we get 4 over B equals A. Okay, and let me move these A and B so I have more room. Okay, and then I take that value of A and I substitute it in right here, so I get 7 equals 4 over B times B squared. Hopefully you recognize quickly that you can cancel there and there. So you get 7 is equal to 4B. Okay, you solve for B, B is 7/4. Okay, so B is 7/4, not too bad. We now know B is 7/4. By the way, 7/4 is, well, if you want to think of it in terms of a decimal, 7/4 is about 1.75. And notice that's approximately what B was here. Now it's not exactly, that's what it was the first time, and obviously that's 7/4. Now we could have done that just by figuring that out. Hey, but that's okay, we've got it. Okay, and then we substitute this in for our B term right there, right? And so, and I'll go ahead and do that math. Right here we get 4 over 7/4 equals A, or 4 over 2.25 equals A, or A equals 16/7. Which, by the way, A, if it's 16/7, 16/7 is approximately 2.29. Okay, so that's going to help us later. So when I write my equation, I'm actually going to use the decimal form this time. So I'm going to go y equals 2.29 times 1.75 to the value of x. Now I will tell you that unless they actually ask you to write it in decimal format or round, you should use the exact value 16/7. However, I'm going to be comparing this with some other ones here in a minute, so I'm using the approximation. So if you used your exact values, your actual equation would be y equals 16/7 times 7/4 to the value, or to the x power. Okay? So that's one way to do it. But notice your B term's off. Right? It's off because we know that B could have been, it's going to be probably higher than 1.75 because all these other values, with the exception of 1, was higher than 1.75. So what we could do is this. It's called using transform points. Now, I'm not going to go through the whole math behind this, but if you have a set of points x, y, and we know that it fits a pattern, an exponential pattern like this one did, using the same points. Okay, so in our previous example, we had these. The transform point takes x and the log, or the natural log of y. And if that's a linear pattern, then an exponential model is a good representation. And you can figure out your B term better by finding using the equation of this line. So what I've done is I've done a lot of the legwork here. I've said, okay, my original set of points from my previous problem. I'm going to take the natural log, I'm going to add a row here, and the natural log of y is that row. So really what I'm doing is I'm saying, okay, this row, natural log of y, is just saying, what is the natural log of 4? Well, it's 1.39. What is the natural log of 7? It's 1.96. Natural log of 12. Natural log of 22. Natural log of 39. Natural log of 69. Natural log of 122. Okay? And notice when I plot, this is my x value, this is my ln y right here. Okay, when I plot this and this in an ordered pair, so instance 1, 1.39, okay, 2, 1.96, and so on, this is my graph. And notice that it's linear, okay? And so, or pretty much linear, okay? And so what I'm going to do with that is I am actually going to write the equation of that. I'm going to use this and this data to write an equation of the line there, okay? Well, it works like this. I know that the slope, in order to write an equation of a line, I need to know m and I need to know b. Okay, give myself some room here. M and b, right? Just linear equation. So I can find m. The easy way to find m is just to pick 2 points on a graph. So for instance, those 2 points. Okay, and look at x sub 1, x sub 2, and then rather than calling it y sub 1, it's ln y sub 1 and ln y sub 2. And you can use your slope formula then, right? So you know y2, which is now ln y2, minus y1, which is now ln y1, over x2 minus x1. That is your slope. That's your slope equation, right? So if you think back, slope is equal to y2 minus y1 over x2 minus x1, back from algebra days earlier this year when we dealt with this. Okay, well that's all I'm doing here. So I'm substituting these values in. I end up with 1.96 minus 1.39 and 2 minus 1. And my actual slope is, when I do the math, 0.57. Okay, that is in. All right. So now I need to know B. Or the other thing I could do, if I want to forget about B and not even worry about B, I could use what's called point slope form. So remember point slope form. That says y2 minus y, excuse me, not y2, y minus y1 is equal to m times x minus x1. And rather than having y and y1, remember I'm now at ln y and ln y1, right? So I'm going to use that. I'm going to say, okay, well, ln y minus ln y1 is equal to m times x minus x1. Okay, well, that is ln y minus, ln y1 is 1.39, equals m, which is 0.57, I just found that, times x minus, well, x1 is 1. So now if I start simplifying this, I get ln y minus 1.39 equals 0.57. I'll go ahead and distribute that. X minus 0.57. Okay, so I distribute there and there. 0.57x, 0.57. I'll move that 1.39 over, so I get ln y is equal to 0.57 x and minus, or actually plus, 0.82. So I add 1.39 to both sides. Now some of you may start recognizing how I'm going to get my equation here. Okay, now look, I have the natural log of y equals this. How do I solve for y? Well, I have to move this natural log over. When I do that, it becomes base e. So I have e, I need to write it in exponential form, to the 0.57x, this is all now a power, plus 0.82. Okay, just so you know, that is pretty darn ugly. Because what actually happens here now is you are adding in an exponent. And remember, when you add powers together with a base that's the same, really that can be broken up into this format. This really says e to the 0.57x plus, or excuse me, not plus, but times e to the 0.82. right? When you're multiplying powers that have the same base, when you're multiplying exponents that have the same base, you add their powers together, and that's what we did. So we're kind of undoing that. Why would we undo that? Well, because if I rewrite this so that I put the 0.57x in the back, gives me e to the 0.82 times e to the 0.57x. Notice here's my variable back here. This, let's go ahead and take this. This is my a term. Why is that my a? Because I don't have a variable with it. This is my b term. And notice I didn't put the x because the x is up there. So this is y equals a times b to the x now. Just a is ugly, right? A, we're going to have to round it. That's e to the 0.82 is actually about 2.27 rounded. And b, well, b is e to the 0.57 power, which is 1.77, all to the power of x. That is the equation of this data right here now. Kind of crazy. But I want you to notice, look at this equation, 2.27 and 1.77, and our previous equation, 2.29 and 1.75. Pretty darn close to each other. Okay. The third way, and the way that I would probably do this problem, I'd either do it the first way or this way right here, is I'd use a graphing calculator. All right? And this says find an exponential model using graphing technology. And so I'm going to pause here. I'm going to try this graphing calculator that I found online just so that everyone can see it. This is a TI-83. Now I know a lot of you use TI-84s. And we won't forget down here where it says use a graphing calculator to find it, and then use the new model as well as the two previous models to estimate the value of y when x equals 8. We will do that. But I want to show how to use your graphing calculator to do this. Okay, so first thing I'm going to do is on my calculator, TI-84 works the same. I'm going to enter this into a statistics. Okay, so I'm going to click on stats and click on option 1, edit, and I'm just going to enter these points. So in list 1, I'm going to put 1, 2, 3, 4, 5, 6, and 7. Okay, list 2, I'm going to enter 4, 7, 12, 22, 39, 69, and 1, 22. Okay, and then I'm going to hit second mode, which is quit. I'm going to go back to stat, arrow over to calculate. Go down to, notice they want us to write an exponential model. The exponential model for this is we're going to find exponential here. Let's go ahead and scroll down. And exponential regression, EXP. Okay. And I hit enter. And it's waiting for me to keep hitting enter. And there we got it. Y equals AB to the power of x, and they're telling me A is 2.22 or 2.23 if we round it, and B is 1.77. Okay? And so knowing that, let's see if I can switch my computer around so I can write on the screen. Sorry about that. Don't mean to make everyone sick looking at that. There we go. Okay. And so really, in the form here, we have y equals, I lost my 2.23 times 1.77 to the power of x. That is our model with this. Now using that in our previous two models, let's get our previous two. So we had y equals 2.27 to the times 1.77. To the power of x, and we had our first one was y equals 2.29 times 1.75. Switch colors there. To the power of x. estimate the value of y when x is 8. So really that's just straight substitution now. Okay, so y equals 2.29 times 1.75, and rather than x we have 8th power. Okay, and so that would give us y, let's approximate there, let's go to the nearest hundredth, so y is 201.44 here. Okay, and then switching up the colors, we'd have y is equal to 2.27 times 1.77 to the power of 8. Okay, so that's y is equal to 218.68. That's an approximation as well. And then our last one, y equals 2.23 times 1.77 to the power of 8. Okay, so that's also an approximation of 214.83. Notice our last two are really close, a lot closer, much more so than the first one. Notice our b term in the last two were very similar. Okay, the a was off just a little. Okay, and that's because when you use that natural log model, you get a closer value. This, when you use the exponential regression, which is what you're doing here on your calculator, really it's using correlation information to calculate your equation. Okay, so it's using residual data that we haven't got to that yet, but it's definitely something that you'll get to, especially if you study statistics there. Okay, and so those are our three. I'd use the graphing calculator if I have the ability. If not, I would use this method. I know that this one is not quite as accurate as the middle, but the middle one is just very complex. It takes quite a while. Okay. All right. Hey, one last one, finding a logarithmic model using graphing technology. So it says use a graphing calculator to find the logarithmic model in the form of y equals a plus b to the natural log of x for this data. Use the model to estimate the value of x or y when x is 0.005. Okay, and so once again, I'm going to open my graphing calculator up, so I'm going to pause you here. Okay, so I got my graphing calculator. Like it turned off, so I'll turn it back on there. I'm going to go ahead and enter my my list. I'll go to stat here. There we go, stat. We'll hit enter. If you want to clear out that, just go up to L1 and hit clear, and then enter. Cruise on over to L2 at the top here. Don't hit delete, otherwise you actually delete your list, but clear and then enter. There's other ways to clear those, but it's a pretty basic way. So my data for list 1, I'm going to put my x's. So it was 1, 0.45, 2, 0.09, 0.045, and 0.02. Okay, and for my y's, I've got 0, 5, 10, 15, 20, and 25. Okay, and so from there, if I go ahead and quit and go to stat, notice they're actually asking us for the natural log. So I'm going to go ahead and go over to calculate, and I'm looking for the natural log. Okay, and there it is right there. So option 9. Okay, it gives me my regression equation, y equals a plus b to the natural log of x. All right, so we had a is equal to negative 0.15 if we go to the nearest hundredth. B is equal to negative 6.42 to the nearest hundredth. So that gives us an equation of y equals negative 0.15 minus 6.42 ln x. All right, so there's our equation. And what is y? The value of y when x is 0.015, and it's just straight substitution. So y is equal to negative 0.15 minus 6.42 natural log of 0.005. And kind of squeeze that in there. Let's make it a little clearer. All right. And so calculating that out, actually doing the math on it, y is approximately 33.87. All right, very good. Hopefully that helps out. And I will say that using the TI calculator is probably the easiest route to go on that. I know you can use other forms like Desmos, but the good thing about the Texas Instruments, the TI-83 and TI-84 Plus, is that the College Boards still let you use those. So, or let you use those, whereas Desmos you can't, unfortunately. So I know I show a lot of using Desmos. I was able to find this version of the graphing calculator online for at least just so I could show you guys how to do it using that. I'm not sure that I use it for anything else in terms of online use, but it's a good teaching tool, so I could show you guys how to use that. So hopefully it helped out. All right. Well, good luck.